So pretend you're part of a psychology experiment. You walk into a room, sit down at a desk, and the researchers there show you 4 cards. They tell you that each card is a letter on one side and a number on the other. Your task is to figure out which cards you need to flip over to test this rule. If there's a vowel on one side of the card, then there's an even number on the other. I'll give you a few seconds to think about it. Okay, if you picked the E and 7 cards, you're correct. Now let me explain why. If you flip over the E card, it can either have an odd or an even number. If it has an even number, it supports the rule. If it has an odd number, it disproves the rule. If you picked the 4 card, that's incorrect because the rule only mentions vowels and even numbers, not consonants. So flipping over the 4 card might show a vowel, which is fine, but it doesn't really test the rule thoroughly. It just shows that the rule works in this specific case. Now, picking the K card is also incorrect. The rule doesn't say anything about consonants, so a consonant could be paired with either an odd or an even number. It doesn't tell us really anything useful about the rule. But flipping the 7 card is correct because if you find a vowel on the other side, it breaks and disproves the rule. When testing any rule, we should look for examples that don't fit, because that would prove the rule is wrong and incorrect. Finding examples that match the rule only shows that it works in those specific cases, but it doesn't prove it universally. This is called the falsification principle, which says to test a rule, you need to look for situations that could falsify it. So prove it false, basically. This experiment is known as Wason's 4-card problem. Wason asked participants the same question I just asked you. Out of all the participants, 53% chose E, and 46 thought 4 was also necessary along with E, but only 4 got the correct answer of E and 7. So if you didn't choose the right cards, don't feel bad. Most people didn't either. Testing abstract rules like this are definitely more difficult when not applied to real-world scenarios. A real-world example is if you're shown these cards: beer, soda, 16 years old, and 24 years old. You're told that each card has an age on one side and the name of a drink on the other. Which cards would you flip to test the rule? If someone is drinking beer, then they're over 21. I'll give you a second to think about it. Okay, so if you picked 16 years old and beer, you're correct. If the beer card has an age under 21 on the other side, it disproves the rule. And if you flip over the 16-year-old card and find beer, that also disproves the rule. Both of these experiments test someone's reasoning ability, specifically deductive reasoning. This type of reasoning starts with broad principles or rules that can be used to make logical predictions about specific things or events. If deductive reasoning is used correctly, the prediction should always end up being both true and accurate. The basic form of deductive reasoning is called syllogism, which Aristotle introduced way back in ancient Greece well over 2,000 years ago. A syllogism consists of 2 broad statements or premises followed by a third statement called the conclusion. Categorical syllogisms have a statement beginning with all, no, or some. An example of a syllogism is, all birds are animals, all animals eat food, therefore, all birds eat food. By the way, I did have to look it up. I kept saying syllogism in the recording, and I had to redo it. But, it looks like it should be syllogism, but it's syllogism. The true strength of deductive reasoning is that as long as both premises are true and the conclusion logically follows from them, you'll always have a valid and correct conclusion. In this context, valid means the conclusion logically follows from the 2 premises, and the conclusion can't exist without the premises leading into it. For example, if you take the previous syllogism and change it to, all birds are animals, all humans need food, therefore, all birds eat food, the conclusion is no longer valid because the 2 premises don't logically follow into the conclusion and flow into it. But deductive reasoning isn't perfect. A problem with deductive reasoning is that using it can be very confusing very quickly, because a syllogism can be logical and valid even if it's technically untrue. So, if you're working with incorrect information, deductive reasoning could lead you to an incorrect conclusion. For example, all birds are animals. All animals have 4 legs. Therefore, all birds have 4 legs. The syllogism is technically logical, but it's untrue. So while this conclusion is false, it's still valid, because the premises logically follow into the conclusion. Another weakness of deductive reasoning is that something can be true without being valid. For example, all the students are tired, some tired people are irritable, therefore, some of the students are irritable. This is invalid, because there's no way to definitively state that some students are irritable. A conclusion found through deductive reasoning should be accurate and certain. Since only some tired people are irritable, there's no guarantee that any students will be irritable, even if they are all tired. People often mistake the previous statement as both valid and true because of something called the believability bias, which is a cognitive bias where a person believes a conclusion to be valid and accurate based on their own previous knowledge and experiences, instead of the logical validity of the statement. Basically, it makes sense to them. Maybe they went to college and experienced being a sleepy student, or saw the people around them being exhausted and irritable. For deductive reasoning to be both valid and correct, the conclusion must be a fact that can't be disputed. An example of using deductive reasoning to find a conclusion that can't be disputed, that everyone should recognize, is math. More specifically, algebra. Look at this example. If you have 3x equals 12, to find x, you divide the 12 by 3, to find that x equals 4. This is undisputed. For both sides of our equation to be equal, x must be 4, since 3 times 4 equals 12. The opposite of deductive reasoning is inductive reasoning. While deductive reasoning starts with broad principles to make logical predictions about specific cases, inductive reasoning is the opposite. It starts with specific cases and generalizes them to broad principles or scenarios. While deductive reasoning aims for a conclusion that is both valid and true, meaning you can say with utmost certainty that your conclusion is accurate, inductive reasoning is more comfortable with generalizing. This is actually its biggest strength, because with inductive reasoning, you can identify trends and correlations which you can then use to make inferences and predictions. An example of inductive reasoning is statistics. When statistical analysis is used to make a conclusion, that conclusion typically can't be guaranteed. Instead, it's more of a correlation or a broad trend, or a probability. A study might find that the average teen who uses social media for more than 9 hours a day gets worse grades, but most of the time you can't guarantee that every student who uses social media for that amount of time has worse grades, just the general trend. There could be a student who uses social media for 12 hours a day and is still at the top of their class. Inductive reasoning uses samples to make assumptions about a population. For example, if you have 20 marbles in a jar that you can't see into and wanted to estimate the colors of the marbles in the jar and how many of each color there are, you could remove a sample of 10 marbles from the population of 20. If you find that 7 are white and 3 are black, you might estimate that there should be 14 white marbles and 6 black marbles, based on what you've observed from the sample that you took. While inductive reasoning is often useful and can help estimate facts about a population based on a sample, it does have a pretty big weakness, which is it's still only an estimate. For example, if you expect to find 6 black marbles and 14 white marbles in total, but then you remove the other 10 marbles from the jar, they could be all red. Since you only took a sample, you could have just happened to miss all the red marbles because you got unlucky with the sample you took. If someone doesn't take an appropriate sample, it can easily lead to skewed generalizations, or just general inaccuracies about the population if the sample is biased and not representative of the population. There are ways to counter this problem, though. The main way is by taking a larger sample. The larger the sample, the less likely it is that the sample doesn't represent the population. Increasing your sample size dramatically decreases the chance of an error. It's generally accepted that the smallest a sample size should be is 30. This is because it's the minimum size a sample can be and still create a normal statistical model. Of course, sometimes you can't have that large of a sample, like going back to the marbles in a jar. If there are only 20 marbles in total, you can't take 30 from the jar. So now we've gone over deductive and inductive reasoning, and how they aren't perfect. I wanted to touch on a specific error that is similar to the believability bias, which is the confirmation bias. This is when we start looking for information that backs up what we already believe and conveniently overlook anything that doesn't fit our narrative. Confirmation bias is when people tend to look for information that only supports what they already believe and ignore anything that might prove them wrong, even if they're not intentionally ignoring the things that prove them wrong. If someone believes that lefties are more creative, they will probably only look for proof that supports their belief, instead of looking for information that can disprove their belief. It's as important or more to look for information that disproves our beliefs, instead of only looking for what affirms them. If you've watched this far, I'd like to say thank you, subscribe for more content, and leave a like if you've enjoyed. Leave a comment about any thoughts you have about the video, and any other psychology topics you'd be interested in me covering in the future. Until next time, I hope you have a great rest of your day. Goodbye.